So today I'm going to be going through Stokes Theorem. Well, Stokes Theorem is the generalized version of Green's theorem in standard form. Right? So while Green's theorem is able to help us solve integrals in 2D, with Stokes theorem we can solve problems in 3D. So Stokes theorem is the extended version of Green's theorem into 3D. Right? You can think of it as that way. And this is the formula for the Stokes theorem. So another important factor to note here is that the Stokes theorem relate the line integral on the left side of the formula to the surface integral on the right side of the formula. So meaning here you can find either the line integral or the surface integral depending on the given information, right? And you can note that here we have a new factor called curl, right? Curl of f of bar, right? Which I wrote the formula over here above on how you can calculate your curl, right? So this is just like taking the partial derivative of the continuous components of f bar at x bar, right? So over there. So with that said, I'm just going to jump straight into the example that I'm going to be going through today. So I have two examples exactly, so I'm just going straight to example 1. So the question says evaluate this integral where c is the intersection of the surfaces x squared plus y squared equals to 1 and z equals to x squared, oriented anti-clockwise, and we told that our f bar is given by this. So the other important factor is to always note the orientation of your curve, right, of your region C. So when they say your region C, it's anti-clockwise. It's the same as saying that it's positively orientated, while if they say it's clockwise, that implies that it's negatively orientated, so you must put a negative in front of your integral in order to counter for the negative direction, right? So in this case it's anti-clockwise, so we don't need to counter for the negative direction, so that means positively orientated, so we just go straight into the formula and solve it. So into the solution, so the first thing that I did is to first calculate my curl, right? So curl is taking the partial derivative of f bar, right? So you take the partial derivative of the third component with respect to y, so this is just z squared, so you get 0, minus you take the partial derivative of the second component with respect to z, you get y squared. 0 minus y squared is minus y squared, and you take the partial derivative of the first component with respect to z, you get 0. Take the partial derivative of the third component with respect to x, you get 0, 0 minus 0, it's 0. Then you take the partial derivative of the second component with respect to x, you get 0. You take the partial derivative of the first component with respect to y, you get x. So 0 minus x, it's minus x. So this is our curl here. So curl is a vector field, right? I mean, it's a vector function. So with that said, and remember here we're dealing with surface integral. So our surface is a normal, so we're gonna need to define our normal vector. And over here I did write the formula of the normal vector, right? So our g of x equals to z, right? So, and when you do the normal vector, you just take the partial derivatives of g of x, which is equals to z. So in our case, our g of x, y equals to x squared, and when you take the partial derivative with respect to x, you get 2x, right? So since there's a minus, it just becomes minus 2x, with respect to y, you get 0, and then there's just that one over there, right? Which is, you get this, right? So this is kel, and this is our normal vector over there, and you take the dot product over there, right? So count down for the dot product. So you take the dot product, you're gonna get this, right? So over here, I use polar coordinates to then solve this integral here, right? So with the polar coordinates, remember our x equals to r cos theta, our y equals to r sine theta, right? So we were given the surface over here, right? The surface over here, x squared plus y squared equals to 1, which is a circle with radius 1. So which are all over here. So that means our r is between 0 and 1, right? And our theta will be from 0 until 2 pi, because that is just a circle, right? So a circle is like a little bit bad, but that's just a circle, which is a revolution. So meaning theta revolves around the circle, right? So it's from 0 until 2 pi, right? So with that information, so you substitute it over here. So where there is x, you put your r cos theta. Where there is y, you put r sin theta over here, and don't forget that r there. So we integrating it with respect to r and then theta, right? So first things, you integrate the inside part from 0 to 1, you're gonna get this, right? And then you integrate this part with respect to theta from 0 to 2 pi, you're gonna get 0. You can note that your anti derivative is gonna be in terms of sine theta, and here's gonna be sine cubed theta, and here it's just gonna be sine theta, and sine theta is 0 at both 2 pi and 0. So that makes the whole integral to be 0. Well, there are many ways to like integrate this, right? So that shouldn't be a problem. So let's jump into example 2, right? So example 2 says evaluate this, where C is the intersection of the surfaces x squared plus y squared equals to 2 and x plus y plus z equals to 1 with anti-clockwise orientation. So the orientation of the region C, it's important, it's always important. So you should always check it out before you start your integration, right? So if it's clockwise, so you will know that you have to counter for the negative direction. So the other important thing to note here is that if they just give you something like this means that this part that's inside there, that is your f of bar. You see, I just extracted it directly from here, and I have my f of bar over here, right? So with that said, I calculated my curl here, so you can just use this formula above here that I wrote here for curl, and if you use it, you're gonna get this right over here. You're gonna get this, and then now the important part, you're gonna have z here, right? But then remember, we given that x plus y plus z equals to 1. So if you make z the substitute of the formula, you're going to get that z equals to 1 minus x minus y. So where there is z, you put 1 minus x minus y, which means the third component is by this. So this makes it our curl there, right? So since z equals to 1 minus x minus y, so that means this is our g of x of y, right? So with that said, you can also calculate your normal, right? Since you have your g of x of y. So remember, you take the partial derivative with respect to x and y. So if you take the first partial derivative with respect to x, for g of xy, you're going to get -1, but since it's a negative, it just becomes 1. Same goes for y, and there's just that last 1 over them. And you take the dot product of this, you're just going to get straight this. And then down here again, I'll also use polar coordinates to like solve this, right? So you substitute your x over here, your y, your x, your y again, and don't forget that r over there. And we are also given this surface here, right, which is a circle with radius root of 2. So that means r is between 0 and square root of 2. And theta still moves from 0 to 2 pi because it's just a circle. It's like a revolution. So you substitute everything here, and you take the derivative of the inside part, right, with respect to r, which shouldn't be really hard. You're gonna get this, and then after here, you derive this with respect to theta, right? So you can use integration by parts. Like other ways you can just solve this, but then it should give you 4 pi, right? So that will be your answer, right? So, and below here I left an exercise if you feel like you want to exercise a similar question, right? So with this question they said if so I'm just gonna leave out few hints on how you can just go about solving this. So here they say evaluate this where C is the intersection of the sphere, right? So this is a sphere with the radius 3a, and the paraboloid 2az is given by x squared plus y squared. A is positive with a clockwise orientation, right? So remember that you're gonna need to counter for the clockwise orientation. So it means in front of your integral you're gonna have a negative, right? So to counter for the negative direction, and this becomes your f of x, the inside part. You can just extract it, and then you're gonna have your f bar, right, that inside part over there. And then to get your g of x of y, you're gonna need to solve for z from here, right? So you can solve for z over here. You can see that z will be 1 over 2a times x squared plus y squared, right? And z equals to g of xy, so you can find your normal. And then here you have your sphere, right? So remember, this is the norm of x bar, so that means there it becomes x squared plus y squared plus z squared equals to 9a squared, right? So you're gonna have to solve for z. So with this problem, you can either find the left side, you can find the left side or the right side, depending on how you want to solve it, right? So you can solve for z here first. You can solve for z if, like, you write this is x squared plus y squared plus z squared, and you put the value of z there. You can solve for z first, and then find your circle, and then you can solve the integral. So you can comment below if you're stuck with this exercise, and I'll be glad to comment as I've already done it. So that'll be it for today.